In the last module, we have seen the logic CTL star. In this module, we will see yet another logic for talking about properties over computation trees. This logic is called CTL. CTL will be a subset of CTL star which has efficient model checking algorithms. So you know what CTL star is? We will eliminate certain rules in the syntax of CTL star to get some subset, and these formulas will have an efficient model checking algorithm. So the first task would be to see what this restricted subset is. We will now see what is the syntax of CTL. So let me recall the syntax of CTL star first. We have state formulae and path formulae. State formulae are formed by this set of rules: true, pi, phi1 and phi2, where both phi1 and phi2 are state formulae, not of phi1, and these are the additional operators for talking about trees. This says that there exists a path that satisfies a path formula. This says that there exists, all paths satisfy this path formula. And path formulae are formed using these set of rules. A state formula can be considered as a path formula, and the semantics is that a path satisfies phi if the initial state satisfies phi. If alpha 1 and alpha 2 are path formulae, the AND of them is a path formula, the NOT of a path formula is a path formula, and you have the temporal operators x, u, f, g. Okay, so x of a path formula, alpha 1 union alpha 1 until alpha 2, where both alpha 1 and alpha 2 are path formulae, f of alpha 1, g alpha 1. Okay, so now let us see what are the rules that we are going to eliminate to get CTL. Firstly, the rules which said that alpha could be a state formula, or you can form AND of path formulae and NOT of path formulae, that has been removed. So these three, let us first remove. We will see what are the formulae that go away because of this. But before that, there are more things to be changed. This says that x of alpha 1. When we had this, we could form formulae like x of p1, for instance, because you could have had x of alpha 1, where alpha 1 could have been x of something, and that something could be a state formula which can be p1. So now, since we have removed this, we need to modify this as well to get a base. We will change alpha 1 to phi 1. So instead of saying x of a path formula, you restrict to x of a state formula. So you can say x of p1. Okay, you cannot say x of p1, for instance. Let me do the rest and explain with examples what are the kinds of formulae that are possible. So yet again, instead of writing alpha 1 until alpha 2, we can say a state formula is true until some other state formula is true. About f alpha 1, that changes to f phi 1. Similarly, g alpha 1 changes to g phi 1. So this is going to be CTL. Let us now see what are the kinds of formulae that are possible in CTL. So this is the syntax of CTL. Let's look at legal CTL formulae. You can form EFP1. For example, phi could be E alpha, where alpha could be one of these, f of phi 1, where phi 1 is P1. So EFP1 is a valid formula that can be formed out of these rules. EFAGP1. So see, phi could be E of a path formula. Here the path formula is F of AGP1, where AGP1 is a state formula. See, you can form AGP1, A of alpha, and alpha could be G phi 1, where phi 1 is P1. So AGP1 is a state formula, and then you form one more state formula like this, E of alpha, where alpha is F of some state formula which is AGP1. So you see, EFAGP1 is a legal CTL formula. AXP2, still simple. So A of alpha, where alpha is X of phi 1, where phi 1 can be P2. Okay. You can form AND of two legal CTL formulae. So you can say AFP1, which is possible, AFP1, AGP2, and you can form the AND of them. Let us now see some formulae that cannot be formed using these rules. AFGP1. Remember that AFGP1 is a legal CTL star formula. This says that all paths satisfy the path property FGP1. So this was a valid CTL star formula, but this is not a legal CTL formula because you see, phi can be A of alpha, okay? So if this is formed from this set of rules, then it has to use the rule that phi can be A alpha. Now alpha could be F of phi 1. Okay, now we need to get GP1 here, but this is not possible. No state formula starts with G. Right? You see, any state formula will start with either E or A or just the atomic propositions, and then you can have nots and ands of that. You cannot start a state formula with G. So this is not a legal CTL formula. Although it's a CTL star formula, this is not a legal CTL formula. AP1. For example, look at this. If AP1 is formed from this grammar, then it should have used the rule phi can be A alpha, where alpha is a path formula. Now look at alpha. Alpha needs to have the temporal operators X, U, F or G, but this is not the case. In the case of CTL star, we had a phi here which could derive AP1, but that has been eliminated. So AP1 is not a legal CTL formula. EGFP1, for the same reasons as this, EGFP1 cannot be derived using these set of rules. So if EGFP1 could be derived from here, you should have used the rule E alpha, but then alpha is a path formula, and since you have GFP1, it should have started with G phi 1, but then phi 1 cannot start with F. Okay. What about this? A of FP1 and GP2. Can we do that? If this was a legal CTL formula, then the rule phi goes to A alpha has to be used, where alpha is a path formula. But then we do not have the AND operator here at all. So if this had been a path formula, then you should have had the rule alpha 1 and alpha 2. So this cannot be a legal CTL formula. Let's look at this. A of P1 until EGP2. Is this a legal CTL formula? Let us see. The rule phi goes to A alpha has to be used, where alpha is this formula. It's of the form phi 1 until phi 2, where phi 1 is P1, phi 2 is EGP2. Let us see if EGP2 can be derived as a state formula. Yes, you use the rule E alpha and then take alpha to be G phi 1 and phi 1 is P2. So you have A of P1 until EGP2 to be a legal CTL formula. If you see, this A is associated with this U. When you do A of alpha, alpha is phi 1 until phi 2. So this until is associated with this A. Similarly, this was a state formula E alpha where E is associated with G. Okay. However, this cannot be a legal CTL formula because this is P1 until GP2. So A alpha, phi 1 is P1. Can GP2 be derived as a state formula? No. Since the state formula cannot start with G, this is not a legal CTL formula. This is the thing. Every temporal operator has a corresponding A or E. So if you see this is what I was explaining before. A is paired with this until, E is paired with this G. Here A is paired with F, A is paired with G. Similarly here this A is paired with X. This is how the rules will let you form formulae. Because the state formula would, if it has an E or an A, it should have one of these temporal operators associated with this, because the formula is of the form E alpha, A alpha, where alpha needs to have one of these temporal operators. Here you see there are two temporal operators but only one path quantification operator, A. So this cannot be a legal CTL formula. Same is the case of this one as well. You have two temporal operators but only one path quantification operator. So a legal CTL formula should have corresponding temporal operators for every A and E. Okay. Please try to go through certain examples and check for yourself if that can be a legal CTL formula or not. So here is CTL. In the last slide, we saw the syntax. It's a restricted form of CTL star. And why we need to do this restriction is because this restriction will give better algorithms, and if our properties can be expressed using CTL itself, then the fact that it has efficient algorithms can be exploited. The semantics, that is the meaning of CTL formulae, it is the same as in the case of CTL star. As you see, every CTL formula is also a CTL star formula. So you look at the semantics of that formula that we discussed in the previous module. So this means that there exists a path where at some point of time P1 is true. Similarly, there exists a path where at some point of time you reach a state whose subtree satisfies P1 in every node. Okay? You can work out the semantics for other formulae similarly. So let's look at the mutex example. You have two programs. They are identical threads and they are accessing a shared resource, and this Y makes sure that the critical section is not handled by both the processes at the same time. We have seen this example multiple times. Now the mutual exclusion property is that at no point of time both the processes are in the critical location simultaneously. So how can we write this using CTL? You look at the computation tree. In all paths, in all states, this has to be true. AG, it's not the case that both process 1 and process 2 are in their critical locations. So P1 is the atomic proposition which says that process 1 is in its critical location. P3 is the atomic proposition that says that process 2 is in its critical location. And AG naught of P1 and P3 is the property expressing the fact that both the processes are not in their critical sections simultaneously. Let us now try to check the CTL property in NuSMV. So this is the mutex program, and this module thread is defining the program graph, and you have the main module where you have the variable y and two processes, PRG1 and PRG2. Okay, and the initial value of y is assigned to be 1. The locations in this program graph are non-critical, waiting, critical, and exit. We had checked LTL specifications. Let us now try to check it using CTL. As usual, we do NuSMV minus int, the name of the file, and say go. Remember, in LTL we used the command check LTL spec. Here we will do check underscore CTL spec minus p AG. There should be no space in between A and G. AG. It's not the case that PRG1 dot location equal to C and PRG2 dot location equal to C. Let us now check if this property is true. It says that the property is true. Recall that whenever we used to check LTL formulae, if the specification is false, then NuSMV returned a counterexample. There it was possible because a counterexample would be an infinite trace. Now suppose you check a property on a tree. What would counterexamples be? So in general, you cannot expect counterexamples for all CTL properties. However, for certain CTL properties where the counterexample can be given as a trace, NuSMV will do it. For example, if we check the CTL specification without the not here, so PRG1 dot location equal to C and PRG2 dot location equal to C. Clearly this should be false. Let's see what NuSMV tells. Yes, it says that the specification is false and the counterexample is given to be the initial state itself. The initial state itself does not satisfy this condition. We asked AG PRG1 dot location equal to C and PRG2 dot location equal to C. And a counterexample to this property is that the initial state already does not satisfy this condition. Suppose we check AF. Is it possible that, rather in all paths, is it possible to reach a location like this? Let us see what NuSMV says. Of course, the specification is false. Now, the counterexample to this is going to be a trace, because this condition says, is it true that in all paths at some point of time you reach this condition? If it is not true, that means NuSMV should exhibit a path where this condition is never true, right? And that is what it does. It shows a path here. So that's the loop starts here. You have NC, NC, both of them are in critical locations, and then there is a self loop here. So in this path, this is an infinite path which keeps sticking to this location itself, and nowhere along this path is this condition true. So here NuSMV gives an infinite trace as a counterexample. However, suppose we ask EF, does there exist a path where this is true? Let us see what NuSMV says. It says that no, that's not true. That means what? In all paths, f of this is not true. So here the counterexample does not make sense, because here the counterexample is the entire tree itself. So we cannot learn much out of the counterexample here. So AF, AG, there is some hope for learning something from the counterexample. For EF, the counterexample is just the entire tree. It just says that nowhere this condition is true. Okay? That was a digression to show how one can check CTL properties on NuSMV specifications. Note that this was a property which we could already express in LTL itself. Can all LTL properties be written using CTL? And the answer is no. And this is one such property. This says that, this is a CTL star property. This says that in all paths FGP1 is true. So this can be expressed using LTL formula FGP1. A transition system satisfies FGP1 if all paths satisfy FGP1. And what is FGP1? Eventually P1 is true forever. So you reach a point from which P1 is always true. Note that this is first of all not a CTL formula, because there are two temporal operators but only one path quantification operator. However, the proof that this property cannot be expressed by any formula of CTL is not easy. I will not give the full proof, but I will give some intuition as to why this cannot be captured by certain CTL formulae. So first of all, AFG P1, let P1 be red. AFG red means that in all paths you reach a point from which red is always true. So along this path, in future sometime you would reach a point from where red will always be true. Along this path, perhaps this is the position from which red is always true, and so on. So you look at any path, you will reach a point from which red is always true. Okay, this is the property AFG red. In all paths, eventually red is true forever. What about AFAG? This is a CTL formula. Does it represent AFG? Let's see. AFAG red. This says that in all paths you reach a point from which the entire subtree should satisfy red. This is a stronger condition. Look at AFG red. You can have a tree where these nodes are never colored red. This one, this one, this one, this one, and yet it satisfies AFG red. For example, for this path, maybe the eventual condition starts from here. For this path, the eventual conditions start from the subtree. For this path, the eventual conditions start later in the subtree. So if you look at this nodes, you look at, there are infinitely many nodes which are children of the leftmost path. If you look at this entire set of nodes, it's possible that the set of nodes is not colored red, but still the tree satisfies AFG red. This cannot happen here, because at some point you will reach a node such that the entire subtree below it satisfies red. So in particular, these nodes will have to be colored red. Okay, so this is a stronger condition. Let us now look at another formula, AFEG. Is AFEG equivalent to AFG? It will not be the case. Note that AFEG is a legal CTL formula. However, look at this tree. This leftmost path is colored red fully. Now look at any path. It has a state where EG is true, EG red is true. So look at any path in this tree. Since the initial state has a path starting from it, which is fully colored red, in any path the initial state satisfies EG red. So this tree satisfies AFEG red. Look at this path. It satisfies FEG red because the initial state satisfies EG red. Similarly for all paths. However, clearly this does not satisfy AFG red because AFG red says that in all paths eventually red is true forever. So AFG red is a formula that can be expressed using CTL star and also LTL because it says that all paths should eventually see P1 forever. Here P1 was red and this is equivalent to the LTL formula FG P1. However, this cannot be written using CTL. The proof is complicated. Here I have given you two examples of CTL formulae which are not equivalent to AFG red. So this is the summary. AFG P1 cannot be expressed in CTL. What about the reverse question? Can all CTL properties be written using LTL? Here we ask the question, can all LTL properties be written using CTL? In which case we would be using only CTL. Unfortunately, the answer is no. Now we ask the reverse question. What if every CTL property can be written using LTL? Then we do not have to use CTL at all. And unfortunately, the answer is no here as well. And that is because of this CTL formula. We also saw this in CTL star. So EFAG red, this is a CTL formula which says that there exists a path which reaches a state from which the entire subtree satisfies red. And such a property cannot be expressed using LTL. So here is the relative expressive power of the three logics that we know. LTL is linear temporal logic, CTL is computation tree logic, and CTL star is a superset of both of them. So there are some properties which can be expressed using both LTL and CTL. For example, AGP. I mean, in all paths, in all states, P is true. This is the invariant property. This can be expressed using both LTL and CTL. EFAGP, the one that we saw in the previous slide, which says that there exists a path from which the entire subtree below it satisfies P. This can be expressed using CTL, but not in LTL. And we also saw that FGP, this can be expressed using LTL, but this condition cannot be checked using CTL. However, CTL star contains both LTL and CTL. Now, is there a formula in CTL star which cannot be expressed by both CTL and LTL? Yes, take the OR of this, EFAGP or AFG of some other proposition Q. Now this cannot be expressed using CTL. Why? Because suppose this were expressible using CTL. So this gives us the set of trees that satisfy either this or this. Now suppose there was a CTL formula for this. We know that this is a CTL formula and we can take a knot of this. So look at the CTL formula for this and knot of this. That will be another CTL formula and that will be the formula for AFGQ. Because you take this, you take the CTL formula which expresses this, if at all there is one, and knot of this would mean that this has to be true. And so this is giving us a CTL formula for AFGQ, and that is not possible. Similarly, if there had been an LTL formula for this, you can do a similar trick to say that an LTL formula for this would give us an LTL formula for this, but however we know that that is not possible. Okay, so we have seen a lot of logics in this unit. So CTL is essentially for talking about computation trees of transition systems, and CTL is useful because the algorithms for CTL are more efficient. However, writing CTL specifications is slightly more difficult than LTL. So if you are comfortable writing LTL specifications, and if they are indeed enough for your purpose, then you might as well use LTL. However, if there are properties like this which are needed, then CTL should be used. Here is a summary. CTL is the subset of CTL star where the temporal operators and the AE operators come in pairs. So we have seen the syntax of that, and we gave a comparison of the expressive powers of CTL, CTL star and LTL. So CTL star is a logic which subsumes everything, and algorithms for CTL star are difficult. Similarly, algorithms for LTL are exponential. However, we will see in the next unit that algorithms for CTL are more efficient than both LTL and CTL star. So this is a fragment of CTL star with efficient model checking algorithms. Writing CTL specifications is slightly difficult than LTL. So that is why we have tried to give a lot of examples in this unit. You can try to go through them and become more comfortable in writing CTL specifications.